Hello, this is Professor Mulford, and I want to talk to you about the question of how to make a buffer. And there's really two parts to this video that I want to mention. First of all, just what are the chemical components you need to make a buffer? And then secondly, how do you make a buffer of a particular pH? Okay, so let's think about this first question. What do you need to make a buffer, right? Remember that to have a buffer system, you need to have a weak acid or base and its conjugate. Okay, so there's two ways you can do this. The first one is, well, let's just put both of those things into the beaker. All right, so we've got our beaker here, and we're going to put in a weak acid or base, and we're going to put in its conjugate. So, for example, we could put in acetic acid, and then we need to put in its conjugate. So its conjugate is acetate, and you can't just have an ion on its own. So it's got to have a counter ion. So we do want to make sure that the counter ion is inert. Okay, so we're going to do this. We're going to have potassium acetate. Remember, potassium, conjugate of the strong base, sodium or potassium hydroxide. So it is inert. And so what you're putting into your beaker at this point is the weak acid and its conjugate. Okay, you could do that with a base as well. The second option here is to, so option B here is let's get ourselves another beaker. Now this time what we're going to do is we're going to put in a weak, let's say a weak acid, and we're going to put in some strong base. Now when you think about it, that at first, wait, but we need to have a weak and its conjugate, but let me show you what we do here. We're going to take, say, acetic acid again, and we're going to add to this sodium hydroxide. Now, we have to be careful about how much we put in, because the idea is this. Let's say we start with 1.0 moles of the acetic acid, and we're going to add to this 0.5 moles of the hydroxide. All right, CH3COOH, acetic acid that is aqueous, will react with sodium hydroxide. This is a strong base, so it's going to react completely. And that's going to give us CH3COO minus, and it's going to give us water. I know I'm kind of mixing my net ionic and my whole molecular here, so let's just go ahead and take that sodium off there and make that our hydroxide. All right, so if initially I have 1.0 moles of this, I don't have any of this yet, or any of that, and then we're going to add to this 0.5 moles of the hydroxide, then at equilibrium, this becomes 0.5 moles, that goes down to 0, and this becomes 0.5 moles. And so once again, we have a weak acid and its conjugate. So we have converted some of the weak into its conjugate. And you can do this either with the acid or the base. You just have to make sure that you add less of the strong material than the weak that you started with. Okay? So that's to make a buffer. Either you put the two buffer components in or you put one of the components in and then convert it to the other. The second question that comes up is how do you make a pH of a particular, or a buffer of a particular pH? So buffer of known pH. And this is much more common. Right here in chemistry class, we usually say if I mix this together with this, what pH will I get from my buffer? But when you go out away from this class, it's going to be much more common, say you're in biology, to say, all right, I need to grow these bacteria in a 5.2 pH solution. How do I make that? Okay, so let's look at that. And it all comes down to the Henderson-Hasselbalch equation. pH equals pKa plus the log of the weak acid over, or the conjugate base over the weak acid. Okay. And since pKa is constant for a particular material, that means that the pH is going to be completely dependent upon the ratio. And so that's actually what we're going to get here. Let's look at an example. What if we did want to make that? What if we wanted a pH of 5.2? Because that's what we wanted to test our bacteria with. pH of 5.2 with the acetic acid buffer. How would we do this? Okay. Well, we can look it up, and we say, all right, we need a pH of 5.2. Oh, come on. Okay, we need 5.2. And we then look up the pKa, and that's 4.75, plus the log of A minus over HA, right? And for us, that's acetate over acetic acid. In fact, let me go ahead and put that in. All right, so we're going to say the log of CH3COO minus over, okay? Well, we do a little calculation here, and what you'll find is that you get a ratio of CH3COO minus, oh, that's a lot of O's there, over equal to 2.82. So this tells you that the ratio of the acetate to the acetic acid is 2.82. Remember, that's 2.82 to 1. Okay, so you need 2.82 times as much acetate, which if you think about it makes sense, right? The pK is 4.75, and that's when they're equal to each other. We need to be a little more basic. We want a little higher pH, so we're going to have a little more of the base there. Now, it does not tell you the absolute amount. As long as you have this ratio, you'll have the right pH. You could have 2.82 moles of acetate and 1 mole of acetic acid. You could have 282 moles of acetate. Okay, that's getting ridiculous. And what do? We multiply by 100 and then 100 moles of the acetic acid. As long as you have that ratio, you'll get that pH.